to our talk this evening. We are honoured to be hosting Tito Semler for his talk on climate modelling. He has had an interest in weather since he was a child and studied meteorology in Berlin and did his PhD thesis about regional climate modelling at the University of Hamburg. After completing his postdoc, he moved to Met Éireann and worked there for 8 years. And then after that, he spent 11 years at the Institute for Polar and Marine Research in Germany, where he was able to get more insight over the oceans and an important part of the Earth system and therefore for the climate. And now he's back working at Met Éireann as a senior research fellow in climate modelling. So thank you and welcome.
Thank you, Kiva, for the nice introduction. So, first, of course, I should say that the whole thing is a group effort. So, it's basically the climate modeling unit at Met Éireann. So, myself, I'm Tito Semler, and my colleague Enda Odi, he's here in the audience. Markus Todd and John Henley, who cannot be here in person. And yeah. So, just to give you a little bit an overview what I would like to talk about to you. So first of all, why do we actually do climate modeling? And then what is a climate model? How does it work? And then we go a little bit more towards our region here, the role of North Atlantic for Ireland and advanced approaches to refine the climate projections for the North Atlantic and also for Ireland, and give some sample results and conclusions. So, okay, I think many of you probably know this. Just to tell you once more, why do we do climate modeling? Of course, obviously we know from the IPCC, which is the Intergovernmental Panel on Climate Change, the synthesis report published in 2023 here depicted the title page of the summary for policymakers, that human activities really through the emissions of greenhouse gases have caused global warming. So there's really no doubt about this anymore. And now the global surface temperature has reached 1.1 degree above 1850 to 1900 in the decade of 2011 to 2020, and we also already know that really the climate extremes in every region across the globe have been affected already. And of course, obviously here in Ireland, for mitigation and adaptation, we need to know what is going to happen here. So, and then, of course, the mission of Met Éireann, I mean, many of you might know the Met Éireann, the Irish Meteorological Service, as a weather forecasting institution, but actually in the mission of the institute, it says making Ireland weather and climate prepared. So, of course, I'm going to talk to you also what is the difference between weather and climate in more detail. But some of you might know that, just keep that in mind, making Ireland weather and climate prepared. And therefore, of course, there is the climate modelling unit at Met Éireann, which are already introduced. So now, if we want to say, let's talk a little bit about weather versus climate models. So for the weather forecasts, as you all know, we are interested in the course of the day, how the weather develops at a certain location for a certain day. So we want to know, is it going to rain in the afternoon or is it going to be dry in the afternoon, for example. But for climate projections, we are not at all interested in the weather, let's say, of one particular day, the 4th of November 2044. That is not what is interesting for us. But we are instead interested in the statistics of the weather. And that we call climate. So now we know also what is the difference between weather and climate. So there could be the mean temperature over a certain month, for example, a 30-year mean over all Januaries in Dublin. The mean temperature. It could be one climate parameter that is part of the characterization of Dublin climate. So we might also be interested in the maximum daily precipitation per year. So it's not just mean values, but actually the extreme values, because they are much more impactful for the society, this is what even matters more. So this is also part of the climate, the maximum daily precipitation per year, or also the maximum wind speed that might be reached at a certain location over a certain period, usually 30 years. We often say 30 years is a normal climate period, or climate normal. We actually say it, climate normal. So now, what can climate models actually do? So what we know, so since they have been developed since decades, in the meantime, one can really say climate models are very well able to simulate the anthropogenic, this is the word for man-made, climate change to date, but only if we really consider the increasing greenhouse gas concentrations and the changing our aerosol concentrations. Our aerosols, I mean greenhouse gases, you probably all know there could be carbon dioxide or methane or others that trap, like in a greenhouse, the heat at the surface. But the aerosols might be a little bit more, you might not, all of you might be familiar with that. That's basically little particles that can be there through a natural cause. For example, sea salt forms a natural aerosol, but it could be also exhausts from cars, engines, shipping industry, or factories. So for example, black carbon that is emitted into the atmosphere, and that also has an impact on the climate. So what we know, for example, indeed, the global mean temperature increased by 1.1 degrees Celsius is very well represented by the climate models. Also, the increase in frequency and intensity of extreme events can be seen from our climate model simulations, or dry areas getting drier and wet areas getting wetter, and the sea level rise. So there, just the quantification for the sea level rise, that might be a little bit more tricky. I'll get back to that later. But generally, one could first say climate models are really doing a good job in representing what has already happened over the last 150 years, or partly more than that. So here, this is actually something that really shows this statement, or illustrates this statement. So this is taken out of the IPCC, the Intergovernmental Panel on Climate Change report. I had shown you in the beginning the title page of the summary for policymakers of. You can here see basically the observed warming is the black curve. Basically the black curve shows you how the averaged over the whole globe the temperature has developed, and as a reference period we just use the pre-industrial period, and then see how basically the anomalies, so the changes from this mean value over the pre-industrial time has changed over time. And we see indeed the observations arrive at something like 1.1 degree above the pre-industrial mean. And we can now run climate models, of course. So we could, for example, just say, let's not prescribe any increase in greenhouse gas and no changes in aerosols. We just pretend, basically, that our climate system, that there's no really changes in these greenhouse gas and aerosol concentrations over the whole 150 years. So if we make such simulations and only consider natural causes, there could be volcano eruptions that, for example, also emit aerosols, natural aerosols into the atmosphere, or the solar cycle, that is 11-year cycle of the sun that basically has a cycle in the solar output, solar energy output. If one considers all this, basically we end up with a green curve, or a range of green curves, because we have many climate models that basically simulated these conditions. That's why we see here a bulk of green curves, or basically a range of possible solutions from different climate models, and the dotted green line indicates then the mean over all these different climate simulations. So, but we could of course also say, let's put in the greenhouse gases, because we have measurements obviously how the greenhouse gas concentrations evolved over the course of these 150 years. So we put this into our climate models, and what do we see? Basically, the temperature increases even more than the observations. So, but we could also do something that we basically say we only consider the aerosols, the human emissions, like sources could be, as I said, all sorts of engines or factories. And then we see basically that the model simulate a cooling, a global cooling, and that is indeed a known impact of these aerosol particles. So, but now we can of course run our climate models with everything together, and then we see, okay, here this is basically the gray, all the gray area here, or the gray dotted line, that is again the mean over all models. We see very well that that observations and climate models are in very good agreement. Good, and this is of course just to tell you, here in Ireland we are doing climate modeling. Actually, these projections here, I should say this shows you the temperature distribution, or the temperature change compared to the pre-industrial situation for different future scenarios. So we have kind of an early action, maybe a mid-early action, a mid-action, and a late action scenario, where, because of course we don't know as climate modelers how the politics will work in the next decades until 2100. And how society basically will react. We don't know this as climate modelers. So we make kind of different assumptions. For example, this one, if we really make a transformation of the society globally during this decade until 2030, we can make a huge difference in terms of warming that is much less pronounced compared to the late action scenario. So, and I should say, of course, that this is an example. Some of these simulations have been done at the Irish Centre for High-End Computing. I check here in Dublin. Oh no, actually, I should say in Ireland, because it's distributed over various places. But in any case, this is one of the results. So we are active in the climate model. Okay, so. Now, what are actually climate models and how do they work? So, you can say the climate models, actually exactly like the weather prediction models, are based on coupled nonlinear differential equations. And so, basically, these the Navier-Stokes equations, they are these partial differential equations, and they are named after the French engineer and physicist Claude Louis Navier, and also Irish physicist and mathematician George Gabriel Stokes. So there's some Irish background here also in these equations. And you can see, of course, these are basically the equations of motion here, then the continuity equation, which is basically telling the mass continuity, preservation of mass or conservation of mass, and also the conservation of energy goes in here. So at the end you end up with a system of partial differential equations that you have to solve numerically. So that's of course, yeah, as I said, these are the same equations and the numerical weather prediction, and the only difference in the way is that we run the climate forecast model for 100 years, but we don't look, as I said, at individual days, because then you can easily say, how in the world could there walk that we can make precise predictions. Sometimes the 10-day forecasts don't really tell you the exact weather of the next 10 days. So just because, of course, we have a different focus, we don't evaluate, we don't really look at the results of climate models on individual day basis, but really in the statistics. So, and of course, to run such models for 250 years or more, because we usually run more than just one simulation, it really needs huge supercomputers, and also some assumptions have to be made here, some approximations have to be made here to actually solve these equations. So, and of course, what we do have to do, we cannot if we would have infinite computing power, of course we could obviously compute the state of the atmosphere, let's say temperature, and then the wind in U and V direction, which is in east and north direction, and we could, of course, the specific humidity and the liquid water. If we could predict this at every little space, or that could not be done. So we have to actually have basically grid points in our models. So this sketch basically shows you here the atmosphere in grid boxes and the ocean in grid boxes, and then there's here the land, and some different surfaces could be here, glaciers for example. And then you have, of course, here a box, and we want to basically, what we do is we solve these partial differential equations at each grid point, but they are usually 100 kilometers apart in the global climate models. Okay, some more recent climate models might have slightly higher resolutions, as we call it. Resolution is called the grid box size. So very often they are, of course, on regular latitude-longitude grid, traditional around 100 kilometers, and then also vertically higher resolved close to the ocean-atmosphere interface, as you can see here, because, of course, there you have the so-called boundary layer, where you have more dynamic action, and where the friction, for example, plays a role. And yeah, exactly. So the components, I mean, ice sheets, this is basically the land ice. The normal models, or state-of-the-art models, usually have atmosphere, ocean, sea, ice, land, but ice sheets are going to be implemented in some coupled climate models as well. So now, I already told you, of course, that basically we only have this, the state variables, like the basic variables, like horizontal velocity, vertical velocity, temperature, and specific humidity and liquid water and ice water. We only have them on these grid boxes. And of course, now imagine 100 kilometers times 100 kilometers. Of course, not all physical processes can be described by the physical equations on these sparse grid points. Imagine, for example, the formation of a raindrop, or imagine then how maybe some raindrops unite. One says their coagulation, or how they actually how they then first are still kept in the atmosphere and at some stage fall out as rain or snow. So all this can, of course, not be solved on such a coarse grid. So that's one example. The other example is, of course, for example, the convection. A lot can be happening in one grid. So there's the mixing, turbulence taking place here, very small scale structures of air movements that cannot be represented in this 100 kilometer grid box. there's of course basically entrainment into a cloud or detrainment out of a cloud, momentum advection. So many physical processes are really happening in such a grid box. And of course, the simulation of the aggregated effect of all these small scale processes cannot be numerically solved because of computation limitation, but has to be parameterized. So basically empirical relationships have to be developed that basically describe the net effect of all this taking place. So another example, look, and this is actually already getting closer to Ireland here, or to what might be specifically interesting for Ireland. This feature, many of you have heard about it already. It's basically the Gulf Stream and the extension, then the North Atlantic current, basically transporting warm water from the Gulf of Mexico all the way to, for example, Ireland, but also other Western European countries. But what many people, of course, don't know what kind of small-scale features you can see in this current here. So these are so-called eddies. So again, this kind of turbulence in the ocean, and they have, of course, a net effect on mixing and transport of water masses. So again, the net effect has to be parameterized in coarse resolution climate models, because they're in the order of a few kilometers, these eddies. So the next thing that I want to talk about, I have touched on it a little bit when presenting our global climate projections. I have already told you that we ran not just one simulation, but several simulations over these, for example, 250 years from 1850 to 2100. And why are we doing this? So the idea comes again from the numerical weather prediction. Rather than just having one simulation, a bunch of simulations, we call this an ensemble, is created, and then we make a probability forecast out of it. So how probable is that a certain weather will occur in Dublin, for example? So here this would be ECMWF. I should know this is the European Center for Medium Range Weather Forecasting, where I have this sketch from. Here we basically have we initialize the model, let's say we just focus now on one state parameter of it. Let's say the temperature. So we do initialize with some disturbance the system and run then many forecasts, each with slightly different initial conditions. Run it basically over, let's say, 10 days, because we are here talking about weather prediction. And then we end up with a probability distribution function of the temperature, for example, at a certain place. So, and of course, we can also do this for climate modeling. So here, when we now this time look at the black curves, you see exactly that. You see basically for the historical simulation, which is the simulation running here in this case from 1950, but I could have shown it also from 1850, running basically to present day, and running many different realizations with slightly different initial conditions, and you get then a spread, of course, in your different simulations. And then at present day, well, it's a little bit before present day, because the last IPCC report basically took, they had a simulation protocol where in 2015 one needed to change to emission scenarios, so these assumptions, basically what we as humans emit already in 2015. And then we have again bunches of ensembles of the different scenarios. So for example, we see then that the early action scenario warms least until the end of the century, here the mid-early, the late and the mid scenario and the late scenario, and we end up, of course, again here with probability distribution functions at the end of the simulation.
Just ask a question. So, I have this normal. The dependence on the initial conditions, like the width seems to be relatively stable actually. So these systems, if I just change the initial condition a little bit, the difference. So it's not characteristic of a chaotic system.
That's right. Yeah. Here, I mean, on the previous slide, I had actually given you an example. Of where two members kind of go in different directions. So that would be more towards a chaotic system. And indeed, in this case here, it's different. I mean, I should of course also add this initial condition disturbance is just one method. One could also disturb certain physical parameters, like in the parameterizations. As I explained before, they are empirical values, and we have kind of a certain range that we think is physically realistic, and one can disturb those parameters and come up with projections, and there actually you get more surprises. So that has been done, for example, in a very nice project where people from the general public in the UK were engaged in running climate simulations in a coarse resolution on their laptop, actually exactly doing that, but using different physical parameters, and there much stronger surprises actually came out. So yes, this is an example where indeed the system is quite unstable, it's not really close to any bifurcation point or something like this. So okay, now we want to, I have touched on the North Atlantic already, now we want to of course go a little bit more towards the region where we live. So basically the role of the North Atlantic for Ireland. So obviously the North Atlantic is a huge heat reservoir. You know all that water has a high heat capacity and definitely warms and cools, therefore much slower with the same energy input as the air would do. So, and here we just show the difference between the warmest and the coldest month from quasi-observation data over this domain here of Ireland, UK, and some parts of Europe. So, and basically what one sees here, that the difference between the warmest and the coldest month, this is actually averaged over 30 years. I said this before, that of course 30 years is a typical period that we as climate researchers use as a climate period. If we do that, we see that the range in Ireland, and even more so over the North Atlantic, the temperature difference between the warmest and the coldest month, the blue values indicate low differences between summer and winter, and the red ones high differences between summer and winter. You'll easily see that we have a much lower temperature difference between summer and winter in Ireland than in continental Europe. And what we call this usually, it's the maritime climate versus the continental climate. We in Ireland are experiencing the maritime climate, and the Central Europeans the continental climate. So, and of course, obviously, we are here in a zone of prevailing westerlies, which means that the North Atlantic really has a strong influence on it. So westerlies, the wind basically coming from the west to the east. So now we want to talk about something, some ocean circulation. So the so-called Atlantic Meridional Overturning Circulation, we abbreviate this with AMOC. Here depicted in a simplified sketch. So I have mentioned already during the section about parameterizations the Gulf Stream and the North Atlantic Current. They are part of a much bigger global system, ocean circulation system, because actually here in the north, in the Nordic seas and also in the Labrador Sea, waters, these warm waters that are transported into these areas are sinking down, and in the deep sea, basically going all the way across the equator and all the way towards the Southern Ocean, where they then upwell again and go back here. So it's a huge conveyor belt and a circulation that is connected obviously through this ACC. That's basically the circumpolar current around Antarctica. That is connected also with the other ocean basins. So one can also say, of course, it's really part of the global ocean circulation, and that makes, of course, all the oceans connected with each other. So we can never really look at them in isolation. So now there's, of course, a lot of, because this is so important, because it brings the relatively warm water close to Ireland, and there have been actually studies already at least 2 decades ago, if not more, about a possible shutdown of this Atlantic meridional overturning circulation as a kind of tipping point, that if a certain warming, global warming would be reached, that basically this ocean circulation might break down completely, or at least slow down considerably. And you can, of course, easily imagine if that was to happen, what impacts that would have here on Ireland and, of course, other parts of Western Europe, because then you would basically miss all the warm water being transported towards Ireland. So that's why, of course, it's really important to understand the fate of this Atlantic meridional overturning circulation. So this is just some examples what has been observed, because there's a lot of discussion really going on, and also, of course, one major outcome is that so far we cannot really see any clear trend in the AMOC, Atlantic Meridional Overturning Circulation Strength, from the 1980s to today, but there's, of course, also natural variability. So because it is such a complex system, a nonlinear system, you can also really have natural variations that could be quite strong, just inherent to the system. So the northeast Atlantic circulation, for example, has brought warmer subtropical waters quite far to the north, all the way to the Barents-Sea-Kara Sea area, which basically emphasizes how important it is also because the AMOC, or Atlantic Meridional Overturning Circulation, has very often been associated just with one number. That one just measures somewhere in the North Atlantic, basically the stream function, so how much water is flowing to the north and how much water is flowing to the south further down, and regarding this just as one single number. And that is not really a great idea, because one has really seen in the last decades quite some changes in various regions that are different. So, for example, that would be, of course, warmer subtropical waters in the very northern North Atlantic that would kind of be counterintuitive if we would be talking about a slowdown of the AMOC transporting this warm water. So this slowdown has been long predicted by models and is still being predicted, as one can see here. So this is basically again running the climate models for the historical period and then going further. And here the AMOC is indeed just presented at a certain latitude, in using a certain depth, and basically of course just as one number. So, but there one does see quite a robust signal of a decline.
What's the y-axis here?
The y-axis is basically the anomaly of the strength of the AMOC, the Atlantic Meridional Overturning Circulation. So the anomaly here, and it is given in Sverdrup, which is I think million cubed meters. Is that right? Yeah, million cubic meters. So it's of course a huge a huge amount. One should say that the normal values, just to give you a perspective, are something like 15 to 20 Sverdrup. So that's the amount of water that above 1,000 meters is transported towards the north in this certain latitude and measured over the first 1,000 meters, because of course below that you have the opposite flow direction, as I have already explained. So the thing is, of course, for the reasons that we have discussed, that the grid boxes are too sparse, climate models really struggle to represent small scale features of the North Atlantic current. And furthermore, of course, the Greenland and Antarctic land ice melting is often not yet considered in state-of-the-art climate models. And that's why we at Met Éireann are really working on this in collaboration with other institutes. So there was a research core basically for a program running over these years 2022 to 2026, improving EC Earth. EC Earth is the name of one of the global climate models that have been run at Met Éireann and other institutes, basically of the North Atlantic Ocean atmosphere system. So, for example, if one looks again at the Intergovernmental Panel on Climate Change, the sixth assessment report in 2021, this is the observed change from measurements per 1 degree global warming. And I want to point your attention to this blue area, which means cooling. So it's basically here below zero, of course. And we are always talking about global warming, and the rest of the globe obviously is warming, indicated by the red colors. But this one here is the so-called North Atlantic warming hole, where no warming has been taken place. And that has been interpreted as a sign of slowdown of the AMOC, the Atlantic Meridional Overturning Circulation. And if we simulate this with our models, we get a slight signature of this as well, but not really a cooling, just a slight warming. So this while in general one can say the overall structure is very well represented with a stronger warming in the Barents-Sea Sea, for example, and in the Arctic just in general, and also that the oceans warm less than the land because of the heat capacity. All this is well represented. Also the continents warm more than the, yeah, okay, I said this already, than the seas, exactly. So a lot of regional features are already predicted well, but there are some that need further attention. So, and now I should of course also admit that basically the model that we have been using has actually simulated quite a strong warming around here, and basically a far too far south shifted warming hole, if at all a warming hole. So, and that's of course why we want to now use different approaches to address this issue. Of course, I cannot go into too much detail about this because of the time. So, for example, in collaboration with the Alfred Wegener Institute, where I used to work before, basically a finite volume sea ice ocean model has been developed, where we don't actually use these cubes as basically discretization, but we are using triangles, or I should say, of course, they are also going into the depth, so will be prisms, the triangle, and then going into the depth. Then we basically compute velocities, for example, at the blue points, and other state variables like temperature or humidity on the red points. And what is very nice about this approach, we can focus on regions of interest. Here, in this particular example, the area of interest was the Arctic. You can see by the orange and red colors, basically a mesh resolution. Resolution is the distance between one and the other mesh point. We see that this is higher in the Arctic, like in this case 20 to 30 kilometers, and lower in some other areas. And here's just how such a mesh would look like in the tropics. Of course, this mesh wouldn't be ideal for our studies because we are now interested in the current here. So therefore, it's very flexible, this model. We can define it differently. This is quite a high resolution mesh, where we actually go to something like 5 to 6 kilometers here in the North Atlantic current area and around Ireland, while of course dynamically less active regions we represent with maybe up to 25 kilometers. So it means basically that we can concentrate our computing power, because one has to consider that this is computationally expensive. We can really focus this on the areas that we are interested in. I should note the Southern Ocean is also important, so that's why we at least have this in 10 kilometers, because of course obviously, as we have seen, is connected, and there are also other reasons for this that I might not go into details right now. So, and now let's look what actually comes out of these simulations. So the whole thing, this was of course just the ocean model that I have been talking about with this flexible mesh approach. So basically what we did, we coupled it also to an atmosphere model, like every climate model has, as I said before. And even the atmospheric climate model is run in an unprecedentedly high resolution for such global climate model simulations, which is 32 kilometers. And what we see here is, for example, the sea surface temperature change from 2025 to 2049 compared to the reference simulation, where we didn't increase greenhouse gases and didn't change other ozons. So we see indeed the North Atlantic hole comes. So that is at least already a success story. It is also still visible in 2050 to 2074. Since this is the scenario which is very strong greenhouse gas emissions, it considers at the end indeed of the century you don't really find the warming hole, at least not anymore as negative values, still as much weaker warm. So this is one idea, but of course, obviously what is very important generally is the slope currents, because at the slope, like for example the North Atlantic current of course originates at in the Gulf of Mexico, and then goes at basically the coast of the northeastern United States towards the north, and you usually have these strong currents at the slope, because you have to imagine that of course in the interior of the ocean you also have a so-called bathymetry, which are in a way the mountains of the sea. And then you have the problem is if you have a very pronounced such slope, for example, And we have been talking about these regular grid boxes, like cubes. Then, of course, in the normal traditional Z-star coordinate, you really have the problem of steps in your bathymetry. And therefore, of course, one has been trying also terrain following coordinates that basically one says also sigma systems that really follow with their coordinate system along the slope here. But that leads to other numerical problems, like for example, horizontal pressure gradient errors where the slope is very steep. So, and for this, of course, one could see normally, of course, one has one single type of vertical coordinates throughout the model domain, but here the idea that we are exploring in collaboration would be to introduce different coordinate systems. I won't go into the technical details here now, but just give you a little bit of an idea what kind of approaches can be used to try to tackle this problem. So this would be in this idea applied then indeed to the very steep bathymetry that we have kind of here around Ireland, Iceland, Greenland, for example. So that we will test this out as well. Here's as I said, I won't go into details. So that is of course one. We have already two approaches. Either we have the horizontal mesh refined, or we have the vertical mesh refined in a way. And now, of course, there's also another choice if we want to focus on particular regions. So, of course, first we would like to get the North Atlantic very well represented, but we also want to study the influence on Ireland. So, therefore, it can be of interest in the atmosphere to do a so-called dynamical downscaling approach, or also called regional climate modeling approach, where we basically take out the coarse resolution mesh, and at the lateral boundaries we prescribe the conditions for a much finer mesh. So that we can, because of course, as you can see, Ireland here has maybe just four grid boxes or so. So from such a coarse resolution global model, you don't really get any regional details for Ireland. And one can also have so-called double nesting. So you kind of go from the global to an outer regional, and then an inner regional with even higher resolution. And this is, for example, like the orography or the mountains then would look like in the coarse resolution model. Of course, you just see actually a mountain in the middle of Ireland, which is really highly unrealistic. While of course, the higher the resolution is, the better you can resolve some features like the Wicklow Mountains or the mountains in the west of Ireland. So, and how does that work? That's basically called boundary relaxation, because you have to avoid to only prescribe it here, let's say, at the very boundary, but you have to define a so-called boundary buffer, otherwise you will get a lot of noise. And therefore, basically, we mix the solution of the global climate model with the solution of the regional climate model. And the global model has basically 100% influence here at the very border. So this is just basically cross section. So at the lateral border here, the global model would have 100% influence. And then we go just a small boundary, maybe usually 10 or 11 grid points or something in this border, towards the interior of the model domain. And here, basically, from here towards the inner, then the regional model domain would do its own dynamics, and there would be kind of no relaxation, no mixing with the global climate model results. So So, and of course, just to give you an impression, so we saw already the orography differences, but now if we are really looking at the regional rainfall simulation, how many more details you really get, of course, from a 4 kilometer resolution compared to an 80 kilometer resolution. So, and one can in principle do exactly the same in the ocean, which we are also going to try in this North Atlantic project. So we can, for example, for us relevant would be, of course, a focus around this area here, again this Nordic Sea area, but one could also imagine above the Labrador Sea, which is west of Greenland, or other important areas that I have indicated are key regions for the North Atlantic circulation, or the AMOC in a wider sense, the Atlantic Meridional Overturning Circulation. So the approach would be the same in principle like for the atmosphere, but the thing is, one can even use two-way nesting so that not only the global domain would influence the regional domain, but also the other way around, kind of the smaller scale waves or smaller scale movements or temperature deviations that are occurring within the small model domain could also interact with the outer coarser resolution domain. And that, to do that, one will need to run basically the global and the regional climate model at the same time, so that this information can be exchanged. So that that could be even done maybe in one executable, but doesn't need to be. That's of course a difference compared to the traditional regional climate model system, where one first runs the global climate model, saves basically the boundary conditions, which are the state variables like again temperature and wind and so on, and basically then drives the inner domain, the inner high resolution domain then with these results. But of course, obviously then you wouldn't have the interaction with the outer domain. Okay, so now of course we are also doing we are doing these regional climate model simulations, but we also want to give advice to the civil service or meteorological office. We do want to advise the general public and policymakers with what we would expect for the future. So what we basically offer are then standardized climate projections using a large set of global and regional climate model simulations. So as I already said, to make an ensemble of various model simulations. One also, I mean, I indicated before that you can have initial condition perturbation, or you can have parameters of parameterization perturbations, but you could also just consider different climate models, members, or the simulations of them, members of a so-called multi-model ensemble. And this is basically what this is about. So we basically use all sorts of combinations of global and regional climate models, and then to get then the most likely outcome for the future geared towards planning applications. And there's the bias correction method as also a bias correction method applied, because of course none of the models are perfect. They're doing quite a good job, as I indicated, but there's always room for improvement. But for the policymakers, it is of course very useful to take out the biases that we know. And at this stage, this is atmosphere only, but it could be maybe planned coupled at a later stage. That would be then grouped into global warming thresholds in this case. So like, which is of course politically relevant because of all these agreements that you want to maybe try to limit the world global warming to 1.5 degrees. How would Ireland look like in a 1.5 degree warmer world, or in a 2 degree warmer world, or warmer, even warmer worlds than that? And of course, okay, what one sees here actually is the ameliorating effect of the North Atlantic. So basically we get actually, in the world at 1.5 degrees, we get usually temperature increases that are less than 1.5 degrees. So that means Ireland warms less compared to the global average, which of course for Ireland is good news, but in turn, of course, in other areas of the world, the impacts are worse. And we also see this here for the rainfall, especially here one can see that if we stick to the 1.5 or 2 degree world, then we would kind of really still recognize our summer precipitation climate, so our summer rainfall climate, because there's practically no changes. White maps mean no changes, brown would mean getting drier, and blue getting wetter. So exactly, so that's what we can see. So now I come to the conclusions. So we have seen basically, of course, that climate models have already accurately predicted the warming that we have experienced so far. This is also true for Ireland, not only the 1.1 degree global. So we have talked about, of course, the global mean surface air temperature, but also about the increase in extreme events and the dry areas getting drier, the wet areas getting wetter. These are just very few examples. We haven't really talked a lot about sea level change, and that is, of course, also something that is probably quite relevant for Ireland, especially, actually, interestingly, if the Antarctic ice sheet would melt because of the gravitational impact of the Antarctic ice sheet. It's a huge mass that attracts water towards Antarctica and removes it basically from the northern hemisphere, so that if that impact, because a lot of Antarctic ice would melt, then basically some of the water would flow towards the northern hemisphere. While if only Greenland ice melting would take place, then of course the opposite would happen, and actually we might end up here with no regional sea level change unless other parameters change, which they do, because of course obviously we also have the thermal expansion of the water and even this AMOC that does affect the sea level around Ireland. That's another very important point why we need to tackle the AMOC, the Atlantic Meridional Overturning Circulation, and to refine sea level projections for Ireland. So, okay, and of course to refine these predictions we have basically looked at various methods that we want to explore, and we have already explored kind of at least in an initial state, in an unstructured mesh approach for ocean. But we do want, while these simulations are very promising because we can represent the North Atlantic warming hole, we do want to also add the impact of Greenland melting and even Antarctic melting because of the reasons that I have been explaining. So this should be added also on top of the unstructured mesh approach for ocean. And the same would, of course, also, we have also looked at the vertical coordinate refinement. This was more a horizontal coordinate refinement. This is a vertical coordinate refinement to especially get the boundary currents close to the coasts, right? And then we discussed, of course, the dynamical downscaling, also regional climate modeling downscaling approach for the atmosphere and the ocean. Or it could be even done coupled, and we are also working on this to get a regional atmosphere-ocean coupled model that can be fed at the lateral boundaries, both from the global atmosphere and the global ocean model of the coupled global climate model. So, the bottom line here, there's a lot of work to be done to address all these points if we really want to systematically explore this. So, so it would be great, of course, if some of you would be motivated in summer internships, or if there are some very close to finishing the masters in environmental science, computer science, mathematics or physics, there is also meteorologist competitions announced at Met Éireann, and maybe one of you would be interested in applying your knowledge for basically such a project. So that I wanted to spread the news. You can always contact me if you're interested in either an internship or even to apply for one of the jobs at Met Éireann. We do want to extend our climate modeling unit. That is our aim. Thank you very much for your attention.
Can I ask a question?
Yes.
In the previous slide you showed, in what stage are we in that it's unavoidable now?
Sorry, can you repeat it?
In what stage are we in that it is unavoidable?
Which stage are we in that is unavoidable? Yes, I think if we, what we know as scientists, if we make a transformation right now of the global society, so basically getting to net zero emissions or even until 2050, but we would have to really drastically start right now, then we might not reach the 1.5 degree world, maybe something in between 1.5 and 2 degrees. So it is in principle still possible, but it needs a global effort of the whole society. That is of course what we know, and as scientists, but it would be of course up to the politicians to see how one can achieve that in the real world. So we as scientists basically provide what can still be possible. So all these here are basically achievable solutions. This one, of course, with a very, very strong global concerted effort, and this one, in a way, we don't do anything at all, which probably, I'd imagine, could be something in between that we would be reaching. Yes.
Could I ask what tools and what languages are you using to generate these models and these simulations?
Yeah, we are actually still using Fortran, believe it or not. So this is in the scientific world still widely used. So especially in the climate modeling community, sometimes some C or C++ routines are also in there. Yeah. So that's, but for the evaluation, we're starting with Python. But of course, there are attempts actually to write at least some simple climate models in Python language. But that's still very much in the beginning.
It's just on that. Is there some advantage to going to Python? I would have thought that there's something like Julia or something like this would have been something designed for high performance computing, whereas Python.
Yeah, I think these are just.
Yeah.
Yeah, that's why I think that won't really be a viable option, and it is, as I said, only used maybe for some test applications. Right. So it is not really. It won't really happen. That's for sure. That these large-scale computer models will move. So at the moment, actually, everybody still continues with Fortran and C++, but it's very limited. Very few subroutines that might be in C and C++. The bulk of it is really Fortran, yes.
Can I jump in there? There are some efforts to kind of make a higher level language, which is just write in the maths, a bit like in Python, and then it gets interpreted to whatever particular HPC you're using. It's always a nightmare going from one HPC to another HPC, recoding it. But that's the domain of the computer scientists, and we as these modelers don't necessarily want to get bogged down with that. That's not yet the case, but that is an effort.
I thought Julia was meant to be sort of an effort at sort of has it's reasonably high level, and so you're relatively slick for doing sort of but it also can be relatively efficient for. But at the same time, no one else seems to use it. That's
No, otherwise
It's
I
great,
would have.
but no one uses it.
Otherwise I would have known it. Yeah, or rather not necessarily,
No.
but at least it's not done. Let's say, at least it's not done in a large scale effort. That's certainly not the case. Yeah. Maybe some are trying some things. I mean, just not published yet, or I just don't know it.
I know somebody at BICHEC who tried to do it, got so frustrated he left the field altogether.
All right. Okay. Yeah.
So what are the specific advantages of Fortran? Like, it's been around for a long time, but why has it been used for so long and it's continuing to be the dominant tool?
Sorry, why is used?
Well, why is Fortran still like continuing to be used today? Well, what are the advantages of that?
So I think in general it is still a language in which one can numerically efficiently program the code. So it has been originally developed for scientific applications, and it still is very efficient, numerically efficient. So that's the main motivation, because these computer simulations are so expensive, numerically expensive. And then if you would use a computer language that costs 50% more time, for example, that would really be a no-go, because you do want to bundle your resources, and you really want to try to resolve as many processes as possible. Yes?
I think just on that, I think the computer companies, the large computer companies for decades have been putting a great deal of effort into optimizing the compilers for Fortran. So, you know, it just has been getting better and better. I just wanted to ask you, Tito, about regional climate models. It's impressive, of course, when you show the beautiful Wicklow Mountains, and that immediately shows the benefit of a fine mesh. But in reality, things like the fine rainfall prediction, it's not obvious that you're actually getting anything.
Yeah.
Are you convinced that you're really getting value for considerable investment of computing time?
Yeah, and we have had this discussion even internally in our climate modeling unit, because of course while you indeed get the details of present day rainfall or present day temperature because of the orography much better resolved, the change that we project for the future is sometimes, I mean, as you even can see actually on, I mean, here you see of course these beautiful structures that you can resolve because of the higher resolution, in this case because of the rainfall, and not necessarily here because of the orography, but just because of the finer spatial scales. But if you look at this, you really ask the question, could we not have produced the same maps just with the global climate models? So this is a very valid question, and we are basically we have had this discussion as well, and because of course in principle you could come up just basically, you know, of course what the orography of Ireland is, and you basically have observations and you know precipitation patterns, and why not kind of add just the global climate change signal onto basically the regional details of the observations. So you just add the change pattern of the global climate models onto the observed rainfall or temperature of today, and then you come up with a projection. So yeah, we have been discussing this, and of course obviously one could say maybe actually to get the North Atlantic right on the global scale and all the global interactions is even a more important point, because of course even if you have such low probability, high risk events like a complete AMOC shutdown, which is of course at this stage seem unlikely, but if it would materialize, then of course all these projections here are anyway would be in this low probability, high risk, look completely different here. And then should we kind of rather focus, it's a very valid question, should we rather focus on these details, on these more global features, which are details of the global climate system, but not necessarily highly resolved features over Ireland, should we focus more on those? And that could of course still be done with a refinement, both like regional models over that also feed back into the outer regions in the ocean, as I had depicted in this transparency, for example. So it is, yes, it is up for discussion. Yeah, indeed.
What you were mentioning, the pseudo-global warming approach?
Pseudo-global warming approach. This is of course something where the regional climate models can show benefit. So basically, what is the pseudo-global warming approach? That means that there are various ideas around. So the simplest idea is actually let's make everything 1 degree warmer, and look how will Ireland look like this, and that then in a regional model simulation. And we look maybe at a particular storm, and there will be something that will be quite nice even for TV forecasters to say. So it means let's take a look at the storm Debbie that has just passed. So and then we run this, that has been of course also simulated with a regional weather forecast model. And now we run exactly the same simulation again, but we increase, let's say, the sea surface temperature, the ocean surface temperature, and also at the lateral boundaries where we feed the regional model with a global model. Let's increase everything by 1 degree and see how would the storm evolve there. And it could be that it gets more intense because of the Clausius-Clapeyron relationship. Every degree warming, 7% increase of potential maximum rainfall, because it can hold 7% more humidity. So very interesting to see like how that storm would have evolved in a 1 degree warmer world, 2 degree warmer world, 4 degree warmer world, or even in pre-industrial situation, to see how much better would it have been without global warming. And very interesting also could be heat waves. So certain heat wave events could be even amplified, especially on the continent where the soil dries out and you have a positive feedback, which means it amplifies itself. So for example, we made at Alfred Wegener Institute, some colleagues made a pseudo-global warming study in a 3 degree warmer world for a heat wave where Cologne had 40 degrees Celsius. And what was the result? Basically 3 degree global warming resulted in 7 degrees hotter, so 47 degrees in Cologne maximum temperature instead of 40 degrees. And with this, of course, you can also easily show the general public how severe such a 3 degree warming could be, because if you just say it's going to be 3 degree warmer, then people think, oh, so what? Doesn't really matter. But if you make such a simulation, such a pseudo-global warming simulations, then you can of course get much more understanding also from the general public. And for this, the regional climate models, I think, are really a very good application. Yes?
Can the climate models explain why Greenland was green 1,000 years ago?
Why Greenland was green 1,000 years ago?
Yes, when it was discovered.
So I guess, I mean, I didn't prepare particularly now for what happened 1,000 years ago, but there are paleoclimate scientists who are actually investigating these issues. and it is basically about natural climate fluctuations. So if you look at the history of the Earth, you find very warm periods and very cold periods, like you find glaciers, interglacials, and basically all this has been triggered by natural, not human-made events. So that is, of course, there are many climate change deniers which come always with the argument, but what happened? There were always fluctuations. And of course, the important thing here to consider is that at the end, I mean, of course, there have been always changes in the climate, and therefore species have been basically extinguished, right? And of course, we probably ourselves are mainly concerned about the climate change because our own future. Not because it has never been like this before, but because our own future as humans, as the species human. Because animals might get extinct. We might get extinct if it would be very, very bad, which I don't even think it might happen. But of course, the world will anyway live, no matter how the climate changes. You just get other species developed like it has happened in the Earth history. And now, why are we doing all this effort? We could argue it's unnecessary. It was always the case that the climate was changing. But we as humans want to, of course, prepare for it and see what can we do about it to mitigate climate change, to save human lives. So it's from this point of view crucial for us as humanity.
So without human activities, would the temperature go down right now?
No, it would be there would be, if at all, a very tiny trend, I think, indeed, towards colder temperatures, going towards the next ice age, but it is something in the order of 0.05 degrees per century or something like this. So this is, of course, another specialty that climate change deniers often bring up. That basically it has always been happening, but our argument is this time around with the human influence, it is unprecedented how quickly it happens, and that makes it, of course, very difficult for species to adjust to these sudden changes. In terms of Earth's history is sudden, we might say, okay, 1.5 degrees in 100 years, it's quite a gradual increase. But if you compare to the Earth history, this is a huge increase. And this is how we can basically convince the climate change deniers that this is really a very important issue for humanity. Are there any more questions?
No? Okay, well, thank you all for coming.